One of the strangest consequences of relativistic physics is that the mass of a body should increase with its speed, a fact closely related to the impossibility of superluminal travel. While special relativity posits that this phenomenon must be true, the theory has never been able to offer any physical mechanism by which a body of mass should find its inertia increased in consequence of its motion. Hence, there remains no satisfactory answer as to the question of why matter shouldn't be able to surpass the speed of light. Could such a physical mechanism behind relativistic mass really exist? And if so, how might we go about uncovering it? This is Dialect with the problem of relativistic mass. Everyone is familiar with the famous equation E equals mc squared, but there's a secret behind its meaning that's almost entirely unknown. No, it's not just that this equation can be derived classically without any reference to the postulates of special relativity whatsoever, a topic we covered in a recent video, but it's that this famous expression is actually a wave equation. That is, given any classical mechanical wave system under certain ideal conditions, there's a special relationship between the energy of a wave traveling in that system, the speed of that wave, and the momentum the wave imparts in the direction of its travel. E equals P times C. It's a relation found in all sorts of real-world systems, from sound waves in acoustical mediums, to waves on strings, and even water waves to some extent. Now, the fact that waves carry such momentum allows us to do something very interesting. In accordance with Newton's laws, we can divide a wave's momentum p by its speed c, and in doing so, assign that wave a mass m. This in turn yields a second expression for wave momentum, which, when plugged into the expression for wave energy, yields E equals mc squared. Thus, we see what this famous expression is actually telling us, is that a wave traveling with energy E and speed c behaves exactly as though it were a body of mass m traveling with speed c, with m equaling E over c squared. Or, in other words, waves carry a very real inertia proportional to their energy content. Note that none of this requires any sort of spooky space or time relativism. Rather, it all just follows from very basic, straightforward wave mechanics. And such mechanics were in fact the lens through which mass-energy equivalence was first discovered in the year 1900. This was when the French mathematician Henri Poincaré realized that in order for Newton's third law to be reconciled with electromagnetism, electromagnetic waves had to carry both momentum and mass. Subsequently, he was able to show that electromagnetic fields have an inertial density proportional to their energy density, with the constant of proportionality being 1 over the speed of light squared. The implication was that light itself both carried and transmitted mass, a fact next grasped at, but not truly comprehended, by the individual whose name would soon become synonymous with E equals mc squared. Indeed, in 1906, fixated on the idea of mass-energy equivalence, Albert Einstein set out to rederive Poincaré's 1900 E equals mc squared result, though he adopted a much simpler approach. Expanding upon a scenario considered by Poincaré, wherein a body of mass emits a burst of radiation and recoils, Einstein recognized that if the radiation emitted by the body was assumed to carry away only energy and not also mass, then this would lead to the possibility of perpetual motion. To avoid such an outcome, Einstein imposed a stationary center of mass condition upon the system, and subsequently calculated the amount of mass required to be carried away by the radiation to be equal to that radiation's energy content divided by c squared. Now, like Poincaré's proof before it, Einstein's derivation here was entirely classical, and therein lay its true value. But Einstein never understood the full implications of his work. That is, he recognized the first half of the picture, that because bodies exchange, emit, and absorb radiation, their inertia is dependent upon their energy content. However, in his desire to abandon classical thinking, he missed the second half, that this energy content relates to inertia in precisely the quantity that it does because of wave physicality. That is, because light is physically a wave and waves physically carry inertia. This in turn meant Einstein overlooked something remarkable that lay still further in his proof, something which would have yielded all the content of special relativity without requiring any of its postulates: a completely classical derivation of relativistic mass. Now, to be fair, relativistic mass was never truly relativistic to begin with. The idea had begun being thrown around in the 1880s in the context of electromagnetic theory. And by 1904, the correct equations had already been formulated by the Dutch physicist Hendrik Lorentz in his paper entitled Electromagnetic Phenomena in a System Moving with Any Velocity Smaller Than That of Light. The same paper where he published the famous coordinate transformations which today bear his name. Now, while in Lorentz's work, relativistic mass could be classically attributed to the additional energy and momentum carried by electrons in their fields, his derivation relied on the idea that electrons were malleable spheres of charge. Thus, its potential scope and veracity were limited. Now, early derivations like Lorentz's were also not technically derivations of relativistic mass, but rather derivations of closely related concepts known as longitudinal and transverse mass. Now, in Newtonian physics, mass has one and only one definition: the ratio of a body's momentum to its velocity. But when deriving longitudinal and transverse mass, Lorentz and others were actually calculating the ratio of applied force to a body's acceleration, and designating this quantity as mass. But such a quantity is not mass. Rather, it should be more accurately termed effective inertia. Because force, as defined by Newton's laws, is not ma, but rather dp dt, or the rate of change of a system's momentum. This means the ratio of an applied force to a body's acceleration is in truth given by the expression dp dv, which reduces to m only in the instance in which the mass of a body or system can be said to not vary with speed. This overlooked distinction between effective inertia and inertial mass had very unfortunate historical consequences when, in 1906, Einstein's mentor and publisher, Max Planck, became ardently confused about it in the course of giving the first general derivation of relativistic mass. That is, unable to grasp why momentum divided by velocity should give a different expression than force divided by acceleration, Planck wound up haranguing the idea of inertial mass altogether, declaring it to be a degraded concept that hinged on an arbitrary definition choice. This attitude was passed on to Einstein, who later famously declared relativistic mass to be ill-defined. Consequently, today relativistic mass has become something of a dead subject, with physicists often dismissing the idea as outdated, useless, or even misleading. But such an attitude is gravely mistaken, because as Planck and Einstein completely failed to recognize, these different types of inertia already exist in the context of Newtonian physics. For instance, consider the basic example of a rocket ship, which has to eject part of its own mass in order to accelerate. At any one instant, the rocket has a very real inertial mass, P over V, equal to whatever mass is currently in the system. And if the rocket were to shut off its engines and stop accelerating, it would be this value of inertia that would determine its resistance to any further force. However, when undergoing motion, the force required to accelerate the rocket, dp dt, picks up an extra term to account for the momentum of the departing mass. The effective inertia of the system is thus smaller than its inertial mass, because some of that mass departs the system during acceleration. Indeed, like relativistic mass, the mass of a rocket is velocity dependent. And also like relativistic mass, a rocket exhibits a divergent longitudinal mass, aka effective inertia. The perspective we need then to understand relativistic mass is not that a body's inertia magically changes with its speed, but rather that, like an accelerating rocket, in order to change a body's speed, we first have to change its mass. And this is precisely what Einstein's 1906 paper proved. For in demonstrating mass-energy equivalence, Einstein also implicitly demonstrated that a body's change in motion requires a change in its mass, revealing at once the physical mechanism responsible for relativistic mass, a mechanism that will grant us more complete insight into the reason why matter cannot travel faster than light. Three crucial insights are thus needed to explicate the concept of relativistic mass. First, we must recognize that the expression E equals mc squared follows purely as a consequence of wave mechanics, rather than stemming from the postulates of relativity. Secondly, we need to recognize that a body undergoing motion is not a closed mass system, but, like an accelerating rocket, exhibits a continual flux of ingoing and outgoing mass. The last piece of the relativistic mass puzzle falls into place then, once we acknowledge that it is a body's kinetic energy which dictates this precise mass flux. For indeed, if radiation carries mass, then relativistic mass can be explained classically by simply observing the fact that the kinetic energy lost or gained by a body is physically indistinguishable from that body emitting and/or absorbing radiation. That is, imagine a body of mass m traveling at some velocity v that is abruptly brought to a complete halt. Whatever kinetic energy it had due to its motion must now be entirely dissipated into the environment. Well, the theory of electromagnetism tells us that this energy is precisely carried away in the form of radiation, of light. But since that radiation also carries away mass, this means that by losing its motion, the body must also have lost mass, meaning its mass must have been greater in consequence of it having been in motion. Indeed, if its kinetic energy when it was in motion was k, then during the process of coming to a halt, the body must have lost an amount of mass equal to k over c squared. If its mass after coming to a rest is m0, then this in turn implies that its mass while in motion, m, was equal to m0 plus k over c squared. This is relativistic mass. It's not some ill-defined abstraction. It's the literal mass that a body acquires in consequence of its motion. That is, if we have some body at rest and we want to accelerate it via some external force, then what the theory of electromagnetism tells us is that the only method we have available to us is to essentially pelt the body with light or photons. But since these photons are electromagnetic waves, then like all other types of waves, they carry mass. Thus, by absorbing some amounts of these photons, the body is also absorbing a very real inertia, one mediated by the precise quantity of kinetic energy K the body requires for its motion. Now, the kinetic energy K here is not the 1/2 mv² expression that you might be thinking of, because that expression only holds under the assumption that the mass of your body or system isn't changing with speed. But here again, the fact that our body can only undergo motion by absorbing or emitting mass means we are working with a variable mass system, and thus 1/2 mv² no longer applies. Instead, we have to use the strict definition of K, which in infinitesimal form is dk equals f dx, or equivalently, dk equals v dp. If we also want to expand the infinitesimal of momentum dp, then this requires the chain rule. That is, dp equals dmv equals mdv plus vdm. This means the correct expression for kinetic energy in any classical system which features a mass flux is, in infinitesimal form, dk equals mv dv plus v² dm. But from Einstein's proof of mass-energy correspondence, we also know there's a second classical expression for dk, that is, dk equals c² dm. Equating these two expressions, we can rearrange and collect terms to arrive at the following relation. 1 over m dm equals v over c² minus v² dv. Next, integrating both sides and putting in the appropriate bounds, we can solve for m in terms of v. And, well, can you guess what happens? Yes, we arrive almost miraculously at the expression for relativistic mass, and all without invoking a single postulate of relativity. Now, from this expression, the other supposedly relativistic expressions also follow: kinetic energy, total energy, and the relativistic dispersion equation. Meaning the whole arsenal of relativity has just dropped into our laps classically. Here indeed we observe only the consequence of the classical fact that electromagnetic waves carry mass or inertia, and, in being responsible for any externally applied force, consequently must deposit their inertia into ponderable bodies. Thus, when we ask the question, what causes relativistic mass, we can now give the answer that modern physicists can't. Relativistic mass is caused by the absorption of wave inertia by a body in order for that body to undergo motion. This not only reveals the physical mechanism we have been seeking, but it also grants us a deeper insight as to why matter cannot travel faster than light. That is, consider a body with inertial mass m moving at essentially near light speed. We can write its momentum as approximately mc. To accelerate this body further via some external force, the only option we have is to pelt additional photons at it along the direction of its motion. Let's designate these photons as having mass m, speed c, and momentum mc. After these photons collide with the body has a new mass, m plus m, and some new velocity, v. Now, by conservation of momentum, the initial momentum, mc plus mc, must equal the final momentum, m plus m times v. Factoring out the c on the left and cancelling, we see that the new velocity of the system remains c, a result which holds no matter how great the mass of the photons we throw at the body is. This picture, meanwhile, also accords with energy conservation, because with the velocity of the system no longer changing, the change in kinetic energy winds up being entirely dictated by the change in mass. Thus, though true that it requires infinite energy or mass to reach the speed of light, the reason behind this is quite simply that the conservation of momentum in conjunction with the conservation of energy, sensibly indicates to us that no body or entity can be accelerated beyond the speed of the entities which are being used to accelerate it. Now, of course, there's still a lot more about relativistic mass to unpack here, including what the nature of wave inertia ultimately implies. But with this final totem of relativity now classically accounted for, we're at last in a position to deduce the principle of relativity, that is, the empirically observed two-way invariance of light, purely from classical principles alone. Meaning everything modern relativity is required to postulate, we will soon be able to derive. As always, this has been Dialect. Stay tuned.